nodal analysis. Nodal analysis will be used to determine the nodal voltages, and we can also determine the branch currents using nodal analysis. When I talk about branch currents, it basically means the current that is flowing in this particular branch. So in this branch you have this element 5 ohms, right? So the current that is flowing across this 5 ohms resistance can be determined, or I can find out the current that is flowing across this 30 ohms resistance, or the current that is flowing across 10 ohms resistance, this 10 ohm resistance, or the current that is flowing across this 10 ohm resistance, or across this 20 ohm resistance. So all of these are branches that we have seen earlier, right? Whenever you have some sort of a circuit element present over there, you call it as a branch. We can also determine the node voltages. So you have this node, so I can determine this node voltage. Say I name this voltage as V1, I can compute the value of V1. Say I consider this node voltage as V2, I can compute V2. Say I denote this as V3, I can compute the value of V3. An important thing to be remembered in the nodal analysis is we will first always identify the total number of nodes that are present in the circuit. Just two elements being connected, two circuit elements being connected. So this node becomes your simple node, and when you have more than two circuit elements being connected, like the way you have here for V2, so this is your principal node. Similarly, V3 also is a principal node, and then these nodes at the bottom together can be combined as one single node. In general, when we look at the nodal analysis, we consider the principal node and the simple nodes to be called as active nodes. Active nodes, which is both simple node and principal node. And this node at the bottom, this is also one single active node, but for the nodal analysis we will always consider this to be the reference, and this node will be exclusively called as a reference node. So if you have to count the total number of nodes that are present in this particular circuit, when you do not have any circuit element connected between the two nodes, you can consider it as a single node. Actually in total there are 4 nodes. One simple node, that is V1, principal nodes V2 and V3, and this is your reference node, which is another node. So in total the number of nodes are 4, wherein you are considering 3 active nodes and 1 reference node. Moving on, let us see how we can solve the numericals using nodal analysis. So we have 2 cases for this, okay? So the procedure to solve would be, first you need to identify the number of nodes and you need to mark the nodal voltages. So I've considered a similar or same example which I showed you in the previous slide. So I need to first identify the number of nodes, which I have got it as number of nodes to be equal to 4, right? So this is V1, V2 and V3, and this is my reference node. Okay, so total number of nodes is 4. I need to identify how many number of nodal equations I will get. Okay, so the number of nodal equations will be equal to the number of nodes minus 1. Okay, number of nodal equations is, in this case, number of nodes, that is 4 minus 1, that is equal to 3. Now we need to individually apply KCL to these nodes in order to obtain the nodal analysis, because I told you earlier, nodal analysis is mainly meant for determining the nodal voltages. Like we had mesh analysis used to determine mesh currents. So our intention is to determine the nodal voltages. That means you need to determine what is the voltage V1, what is the voltage V2 and what is the voltage V3 in this particular case. And you cannot apply KVL here, so we need to apply KCL. Okay, KCL corresponding to Kirchhoff's current law. So let me explain you how I am going to consider when I am applying KCL. Say for example, you have 2 nodes, okay, and you have an element that is present between the two nodes. So let me denote this node voltage as V1 and this node voltage as V2. And say I give the value of this resistance as say 5 ohms. Generally I will be considering, say I am applying KCL to node 1. So I will always consider that if I am applying KCL to node 1, the current is leaving the node. Okay, the current is leaving the node. So let me denote this current as say I1 using Ohm's law. I is equal to V by R. So I can compute I1 to be equal to, remember I'm applying KCL at node 1. So this equation would be V1 minus V2 divided by the resistance, that is 5 ohm. Okay. Now say I'm applying KCL at node 2. So in this case also, since I am applying KCL at node 2, when I write the equation, I will be assuming that the current is leaving the node. So for this case, let me denote this as current I2. So the value of, or the equation for the current I2 will be equal to V2 minus V1 divided by 5. So in all of these cases, whenever I am applying KCL to the node, unless and until a current source is being specified, I will always consider that the currents are leaving the node. In my analysis, when I am explaining, I will be considering all the currents are leaving the node. So let us look into the first case. Okay. So case 1, you have a voltage source between the active nodes and a reference node. Okay. So to solve a problem in nodal analysis, we first, what we do, we identify the number of nodes, right? So let us mark the nodes here. So this 3 are the nodes, and then I have a reference node. So let me mark the nodal voltages. This is V1, this is V2, and this is V3. This case corresponds to a voltage source present between an active node and a reference node. So if you observe, you have the voltage V1, voltage V2 and the voltage V3, which are all active nodes. I told you, right? Active nodes are nothing but your simple nodes and principal node. And this is your reference node. So you have this case wherein you have a voltage source which is present between an active node and a reference node. So here also you have a voltage source present between an active node and a reference node. So whenever you have a voltage source present between an active node and a reference node, we can directly specify or determine the values of that corresponding node voltage. So here I can directly write this as V1 is equal to Vx, and I can also write this as V2 is equal to Vz. Whenever you have a voltage source present between an active node and a reference node, the voltage would be directly equal to that value. Now for example, say, let me draw another circuit and explain this. So if you look at this particular example, how many nodes do I have in total? I need to count them. So this would be my first node, this would be my second node, right? I need not put a node here because there is no circuit element present. So in total, you have total number of nodes to be equal to 3, including the reference. So this is your active node. Let me mark that. This is V1, this is V2. So these two nodes are your active nodes. So when I look at this particular node voltage V1, this node voltage V1 has a voltage source connected between an active node and a reference node. So when I write the equation for V1, I can write this as V1 plus Vy minus 0 is equal to 0, or V1 is equal to minus Vy. So it is also dependent on the polarity. Simply you cannot apply. I am considering, as I told you, I am considering all the currents will be leaving the node, right? So I will always consider this node voltage to be positive, and I will consider for all of the cases the right hand polarity. So this is V1 plus Vy minus 0 is equal to 0, or V1 is equal to minus Vy. Then moving to the case 2. In this case, you have a voltage source between two active nodes. So first let us identify the number of nodes that we have. So you have in total 3 active nodes and you have 1 reference node. So these 3 active nodes, let me denote it with the nodal voltages V1, V2 and V3. Like we had the case for the mesh analysis where we constructed a super mesh whenever you had a current source present between the 2 meshes. In the case of nodal analysis, whenever you have a voltage source present between 2 active nodes, we call it as a supernode. Let me repeat once again. Whenever you have a voltage source present between 2 active nodes, because in this case V1 and V3 are active nodes, and you have the voltage Vy which is present between them. So whenever you have a voltage source present between 2 active nodes, you call it as a supernode. Okay. So you need to draw the boundary of the supernode in a manner such that you include those 2 active nodes also. So you can see the way I have marked the boundary. So I have included the 2 active nodes. I have not included any other element. You can observe clearly only V1 and V3 node is included, and then I have included the voltage source which was present between them. So this becomes your supernode. So like the way we had for super mesh, we wrote the constraint equation, right? So here also we will be writing the constraint equation. Now in this case the constraint equation will give you the relationship between the node voltages, those node voltages, that is the 2 active nodes between which the voltage source is present. So it gives you the relationship between the node voltages and the voltage source that is present in between them. So this I can write this equation for constraint equation for this particular supernode as, say I'm starting from this point, V1 minus Vy minus V3 equal to 0, or I can write this as Vy is equal to V1 minus V3. So this becomes your first equation, first linear equation. Second thing, we are going to be applying KCL here and not KVL. So you need to apply KCL to the supernode. Okay, so when I say apply KCL to the supernode, you have to consider the branches of all the other elements which are connected to that supernode. Okay, you cannot consider the constraint equation path, you have to consider all the remaining. So say I am starting with the node 1. So what will be the equation for current? As I told you, I have to consider all the currents to be leaving the node, right? All the currents to be leaving the node. So if I start with V1, I can write this as, if I consider this particular branch, okay, the branch R3, I can write this as voltage V1 divided by the resistance R3 plus, all the currents are supposed to be assumed as leaving the node. So this is plus V1 minus V2 divided by R1 corresponding to this resistance. So you have finished writing the KCL for the node 1 plus, because you are applying KCL to the supernode, so you have to consider even V3 because V3 also was included, right? So again in this case consider the current to be leaving the node. So what is this? This would be V3 minus V2 divided by R2. V3 minus V2 divided by R2. Then other than that, you also have an element, that is the current source being connected. Now this current source clearly is entering the node, so you can't do anything with that. So all of these equations were written considering the current to be leaving the node, whereas the current source is entering the node, so this will be equal to 2. So always remember, the equation has to be written in such a way that the currents are leaving the node, sum of currents leaving the node should be equal to the sum of currents entering the node. So this 2 amps is entering the node V3, so it has been written on the right hand side. So this corresponds to your node 3. So this becomes your second equation, second linear equation. Now we have seen, right, that the total number of nodal equations will be equal to the number of nodes minus 1. And the total number of nodes here are, including both reference and active node, is equal to 4 minus 1, which is equal to 3. And so far we have obtained just 2 linear equations. So the third linear equation will be corresponding to applying KCL to the node 2, because that is the only one that is remaining. So on applying KCL to the node 2, we have, this has to be assumed as the current leaving the node. So let me consider this branch. So this will be V2 minus V1 divided by R1 plus V2 minus V3 divided by R2 plus V2 divided by R4 is equal to 0. Okay, this branch V2 minus V1 divided by R1, V2 minus V3 divided by R2 and V2 divided by R4. So we have obtained in total 3 linear equations which satisfy the condition saying the number of nodal equations is equal to 3. Now we need to solve these equations in order to obtain the values of the voltage V1, V2 and V3. This question is meant to be solved using nodal analysis. So you need to, as a first task, determine how many nodes are present in total. So let's count. This would be one node, second node, third node. Okay, and we need to consider the reference node, right? So in total we have 4 nodes. Let us identify which are the active nodes. So this is an active node, this is also an active node, this is also an active node. Let me name them. I will name this node voltage as V1, this node voltage as V2 and this node voltage as V3. And I have explained you 2 cases. One case is where you have a super node concept, another case is where you have voltage source present between an active node and a reference node. So when you look at this particular circuit, you can see you have this 8 volt which is present between an active node and a reference node, right? So let's first find out how many in total number of nodal equations are required. Okay, so number of nodes that we have is equal to 4. Number of nodal equations is equal to number of nodes minus 1, that is 3, that is 4 minus 1 is equal to 3. Now from what we have learnt, we have understood V2 minus 8 is equal to 0, or I can write this as V2 is equal to 8 volt. This is my first nodal equation, right? Then what else can I do? Is there anything else that I can do? No, because we do not have a voltage source present between 2 active nodes. It is just a voltage source, which this is the 8 volt voltage source present between an active node and a reference node. So the remaining voltage V1 and V3 need to be determined. So for that you need to apply KCL to individual nodes separately. Okay, so let us apply KCL to node 1. So what I mentioned earlier was you need to consider that all the currents are leaving the node unless and until a current source is provided to you. So I will assume when I am considering this node 1, this current is leaving 1 ohms branch and this current is leaving the 2 ohms branch. I also have a current source there. Okay, so I can write the equation corresponding to the 1 ohms branch. Yeah, Guru Prasad, tell me, you have any doubt? Guru Prasad? Okay. So I can write this as V1 minus V3 divided by 1 ohms. It is leaving the node, right? Plus this branch, 2 ohms branch, plus V1 minus V2 divided by 2. This current is entering. So KCL, as per KCL, what we have, sum of the currents leaving is equal to the sum of the currents entering the node. Okay, so this is what we have in KCL. And here this 2 amps current is entering, whereas these are leaving, right? So this equation will be equal to 2. That is because the 2 amps current source is entering. So this is your second equation. So we have finished applying KCL to node 1. Now let us apply KCL to node 3. So on applying KCL to node 3, you have, again you need to consider all the currents to be leaving the node. So let me consider this first branch, 1 ohms branch. So you have V3 minus V1 divided by 1 plus V3 minus V2 divided by 4 plus V3 by 4 equal to 0. All of them are leaving, so that is why the right hand side is 0. So this is your third equation. You need not apply KCL to the node 2 because we have already obtained the value of V2 to be equal to 2 volt. So we have obtained these 3 equations, and we have also got that number of nodal equations is equal to 3. So it satisfies the condition. Now solve these equations and obtain the value of V1 and V3. So I can rewrite this equation as 1 by 2 is equal to 0.5, right? So 0.5 plus 1, so this is going to be equal to 1.5 V1 minus V3 is alone, so minus V3, and then you have the value of V2 is 8, so this is minus 8 by 2, that it becomes minus 4. Minus 4 when it goes to the right hand side becomes plus 4, so 2 plus 4 becomes equal to 6. So this is your, let me name this as A. Okay, so this on simplifying, so this is equation B. So solve equation A and B and compute the value of V1 and V3. Use your calculators and solve. Quickly tell me the value of V1 and V3. V1 is 8.8, V2, V3 is 7.2, and V2 is 8 volt that we had determined earlier. So the question was not to determine the nodal voltages but to determine the branch currents. So we need to compute what are the branch currents. So when for the branch currents you need to compute what is the branch current that flows across 2 ohms resistance, across 1 ohm resistance, and what is the current that flows across this 4 ohms resistance and this particular 4 ohms resistance. So let us do that individually. Okay, let me denote the voltages, node voltages again. So to compute the current that flows across this, I will denote this as the current I1. The current that flows across 1 ohms, I will denote it as I2. The current that flows across 4 ohms, I'll denote this as I3, and this current as I4. This was my reference voltage, right? So I1, the branch currents can be computed as I1 to be equal to V1 minus V2 divided by 2. The branch current I2 will be equal to V1 minus V3 divided by 1. I3 will be equal to V2 minus V3 divided by 4, and I4 will be equal to V3 by 4. Now again, depending on how I have marked, the equation will change. Now say you consider the current direction of current I1 to be opposite to what I have marked, then in that case it would be V2 minus V1 divided by 2. So you might get a negative result also. Okay. If I have marked it in this way, I will be getting the answers accordingly. The polarity might change. Okay, polarity might become plus or minus depending on the direction of current you have marked. So it is very important that when a question is asked to you with respect to the branch currents, make sure that you mark how you have considered the direction so that you are sure whether the value is correct or no. The polarity will change but not the value, as V1 to be equal to 8.8 minus we have V2 to be equal to 8 volt divided by 2. So this is going to be 0.8 by 2, which is 0.4 amps. 0.4 amps. V1 is 8.8 minus V3 is 7.2 divided by 1. This is going to be 1.6 amps, right? Then 8 minus 7.2 divided by 4, the value is 0.2 amps, correct? And I4 is V3 by 4, so V3 value is 7.2 divided by 4, which is equal to 1.8 amps. So let's look into next example. So as a first procedure, first identify the number of nodes. Okay, this is one node, second node, third node, and this is the fourth node. So total number of nodes is 4. In that active nodes are marked V1, V2, V3, and the reference node is represented as a ground. Okay, so number of nodal equations is going to be equal to number of nodes minus 1, which is equal to 3. Now when you look at this question, we have seen the two cases. First case was when you have a voltage source between an active node and a reference node. So you can see between V2 and ground you have a voltage source. So the value of this voltage source is obtained as V2 minus, I'll be always considering current leaving, right? So right hand polarity has to be considered. V2 minus 18 equal to 0, or I can write this as V2 is equal to 18 volt. So this is my first nodal equation. Then when you look at this, this is also an active node. V1 is an active node, V3 is an active node. Between V1 and V3 you have a voltage source. So this comes to a supernode case. Let me mark the boundary first. So when I mark the boundary, I need to be very careful to make sure that I include both the two active nodes which were responsible for creating that supernode. Be sure not to include V2, okay, because that is not what is present there, right? So only V1 and V3 were the ones which responsible for creating this supernode. So whenever you have a supernode, you need to write the constraint equation. So write the constraint equation for the supernode. So I need to start from here. So I get this as V1 minus right hand polarity 6 minus V3 equal to 0, or I can write this as V1 minus V3 equals to 6. So this is my second equation. Now for the third equation, what am I to do? I need to apply KCL to the supernode. So apply KCL to supernode. So when I apply KCL to supernode, I need to make sure that V1 and V3 is also included, right? So consider all the other branches for the node V1 and all the other branches for the node V3. So let me start with V1. So how do I write the equation for V1? if it is the branch 6 ohms resistance, you just have that being connected between an active node and a ground. So this becomes V1 divided by 6 plus the second branch. So I need to consider the current leaving. So this is V1 minus V2 divided by 2. So I have finished both the branches connected to node 1. Next I need to consider node 3. So you have a 2 ohms resistance here. So this is V3 minus V2 divided by 2. And then you have a current source which is actually entering the node. So this is equal to 2. So this corresponds to node 3. So you have written the KCL equation for the supernode. So both the nodes are included. So this becomes your third nodal equations. And the total number of nodal equations that we were supposed to obtain was 3, which is very much obtained here. Now, wherever required, substitute the value of V2 and see what you get. So determine all the node voltages V1 and V3. Let's see how we can simplify this. So this equation 3, I can reduce this to, so let us solve the two equations and see what we get. So this would be your equation A and this would be your equation B. So solving equation A and equation B, what do you get? V1 value is 19.82, its value of V3 value is 13.82. So this is V1, V3 and V2. But what is asked in the question is to find VCD, right? So VCD is a voltage which is present between V2 and V3. So I can write the equation to determine VCD as V2 minus VCD minus V3 is equal to 0, or VCD is equal to V2 minus V3. 18 minus 13.82. The value of this is 4.18, right?